This lecture video is about how to solve some equations for specified variables. We're also going to look at learning how to solve some linear equations. And so our first example here, we've hired an architect to design a home. She gives you the following information regarding the installation and operation costs of two types of heating systems, solar and electric. So if you have a solar system, the installation cost is quite high, $25,600, and the operating cost per year is a lot cheaper, $200 a year. For an electrical heating system, the installation cost is relatively low, $5,500, but your yearly costs are a lot higher at $1,600. So we want to, in the first problem, determine the total cost of the solar heating system after 5 years of use. So each year it's going to cost us $200. So 500 times 200 is going to be our cost of running the system. So that would be $1,000. If we're also going to include this installation cost in there, then we have to add the $1,000 to the $25,600. And that would give us a total cost of $26,600. Write a verbal rule for the total cost of the solar heating system, or the output, in terms of the number of years in use, or the input. So the verbal rule is that we would multiply the cost per year by the number of years, and add the installation costs. So that is a verbal rule. Now we're going to let x represent the number of years of use and s represent the total cost of the solar heating system, and then translate the verbal rule that we did in part B into a symbolic rule. So for the solar system, s is going to be our output variable, and our input variable is going to be x, and so it would be, we're going to multiply the cost per year, which was $200, times the number of years, which is x, and then we have to add on to that the installation cost, which was $25,500. Let me double check and make sure I got my installation cost correct. Nope, $25,600. Good thing I checked. Okay, so there's our symbolic rule. Now we want to use this formula to complete the table. And so on the top we have the number of years here, and we want to fill in the total costs. And so we're going to do these on our calculators. And so first, for 5 years, which we already did already, that was the $26,600. And there's a couple things that you might be able to fill this in a little bit faster, because if we go back up here and look at the cost per 5 years is $1,000. So what's going to end up happening here when I fill in my table, because this is going up every 5 years, so we went from 5 to 10 to 15 to 20, and so every increment of 5 years is going to add on another $1,000, which is what we'll see, but I'll do the calculations on the calculator anyways. So we're going to take 200 times 10, and then we're going to add to that the installation cost, which was $25,600. So, oops. So 200 times 10, and then plus 25,600, and we get 27,600. And then do this for 15 years, so 200 times 15. And then we're going to add to that the installation cost, 25,600, and we get 28,600. And do the same thing for 20 years, so 200 times 20 equals 4,000, and then add to that the 25,600. And we get 29,600. Again, every 5 years, the cost for using the system was $1,000, so essentially you add $1,000 for every 5 years, and you could have filled in the table quickly doing that as well. Continue using the information above to answer each of the following. We want to determine the total cost of the electrical heating system after 5 years of use. And so after 5 years of use, it would be this $26,600. Write a verbal rule. Oh, sorry, this is for the electrical heating system. Sorry about that. We need to go back up and look at the information for the electrical system. And so for the electrical system, it's going to cost us $1,600 per year. And we're doing this for 5 years. So we're going to multiply our yearly cost by the number of years. And so that's 1,600 times 5. So that'll be $8,000. And then we have to add on to that the installation fee. And the installation cost was $5,500. So we get 13,500. Write a verbal rule of the total cost of the electrical heating system in terms of the number of years of use. So again, we're going to multiply the number of years of use by the cost per year. And add to that the installation cost. And now we want to write a symbolic rule for this. And so again, we're going to let E represent the total cost. That's our output variable. And this is going to be equal to, so now we're taking X and multiplying it times our yearly cost, and our yearly cost was $1,600. So that's 1,600X plus the installation cost was 5,500. So this is our symbolic rule for calculating the cost of operating the electrical system. And so now we're going to fill in a new table here. And so we already did it for 5 years. That was 13,500. And so again, I'll use my calculator to do it, but the 5-year cost of running this system was, was this $8,000, and so you could just add that on each time, and that would fill in the table for you as well. So we're going to take our yearly cost, $1,600, multiply that by 10. That gives us 16,000, and then add on to that the installation cost of 5,500. And we get 21,500. Now do that for 15. 1,600 times 15. and then add to that $24,000 the installation fee of $5,500, and we get $29,500. And do the same thing for 20 years. 1,600 times 20 gives us $32,000, and then add on to that the installation fee of $5,500, and we get $37,500. When was the total cost for the electric heating less than the cost for the solar heating? Okay. So we need to compare these tables. So I'm going to have to scroll back and forth to look at both tables. In fact, I'll make this smaller so that I can see more on my screen. So we won't have to do quite as much scrolling here. So, and we want to know when was the electrical less than the solar heating. So it's less than for 5 years. It's also less than for the 10 years when you compare the two costs. But now when we get up to 15 years, all of a sudden the electrical is more than the solar. And so and it looks like it's going to be pretty close to around the 15-year mark when that change happens. And so when was the total cost for the electrical less than for the heating? And so that was before 15 years. Not exactly sure right now when that is, but for sure sometime before 15 years, or between 10 and 15 years is where that change is happening. In which years did the cost for the electrical heating surpass that of the solar heating? And so that's 15 years. So after the 15 years, then the electrical is more than the solar. For which year were the costs the closest? And when we look at our costs, so they're really far away that first year. The solar is almost twice the amount of the electrical after 5 years. And then here they're getting a little bit closer. They're only about $6,000 apart, but here they're close to $1,000 apart, and here now they're drifting farther apart as we move away, and so around the 15th year. So at about 15 years. So now use your observations from A to C to estimate when the cost of the electrical heating will catch up to and surpass the solar heating. And so an estimate of that would be between 14 to 15 years. And so I'm going to make my screen bigger now. And so this is not one of the problems in your book, but we want to actually do this calculation to figure out when these costs will be exactly the same. And so what we're going to do is we're going to take the expression for each of these costs and set them equal to each other. So for the electrical, it was this 1,600x plus 5,500, and for the solar, it was 200x plus 25,600. So we're going to take 200x plus 25,600 and set that equal to the 1,600x plus 5,500. And we're going to solve this resulting equation for x. And so what we want to do is we want to get all of the x's on one side of the equation and all of the plain old numbers on the other side of the equation. So when we're doing them in class, I most of the time like to keep my variables positive, but when I'm doing them in class, I'll just always move the variables to the left and the plain old numbers to the right, at least for right now. So if I want to get all of the variables over here on the left, that means I need to undo this 1600x, and the opposite of a positive 1600x is a negative 1600x. So I'm going to subtract 1600x from both sides. And 200 minus 1600 gives us a negative 1400x, and then we have plus 25,600, and it's equal to 5,500. And now we're getting all the plain old numbers on the right, and the opposite of adding 25,600 is subtracting it. And so we'll have the negative 1400x. And I'm going to do this on my calculator. So we have 5,500 minus 25,600. And that gives us a negative 20,100. And the last step then is to divide both sides by the negative 1400. Whoops, wrong thing. And so we want to divide that by negative 1400. And we get 14.357, so about 14.4 years. So somewhere between 14 and 15 years was a good estimate of when these were going to be equivalent. Okay, so now we're skipping a problem or two, and we're going to jump ahead to problem 7, and this is about the NBA basketball court. You and your friends are avid professional basketball fans and discover that your mathematics instructor shares your enthusiasm for basketball. During a mathematics class, your instructor tells you that the perimeter of the NBA basketball court is 288 feet and the length is 44 feet more than the width. He challenges you to use your algebra skills to determine the dimensions of the court. To solve the problem, you and your friends use the following plan. So you let W represent the width of the court, and then you write an expression for the length in terms of the width. So up here in our word problem, it tells us some information about that. It says the length L is means the equal sign, 44 feet more than its width. And so that means that the length is 44 feet longer than the width. So that would be W plus 44. So that gives us an expression for the length in terms of the width, W. Then we're going to use the formula for the perimeter of a rectangle, which is P equals 2 times the length plus 2 times the width, and the information given to obtain an equation containing just, oops, I forgot my T, the variable W. So we're told what the perimeter is up in the word problem. The perimeter is 288 feet. So we can replace this P with the 288 feet that we know the perimeter is. And then it's plus 2 times the length. And here is our expression for the length. The length is W plus 44. And then we have plus 2W. So now we have an expression for the perimeter, and the only variable there is W, and so we'll be able to figure out what the width is of the basketball court. So, in order to solve this, we need to simplify this right-hand side, and to simplify that we need to use the distributive property. So I'm going to multiply this 2 to both the W and the 44. That will give me 288 is equal to 2W plus 88 plus 2W. Now I have two like terms. I have 2W here and a 2W here, so we can add those two together. That gives us 288 is equal to 4W plus 88. And since the only variable I have is over here on the right, I'm just going to leave it there, and I'm going to subtract both sides by 88. That gives us 200 is equal to 4w, and now we want to divide both sides by 4. And so we get the width is equal to 50, and the measurements here were feet. Now we can calculate the length. The length we know is 44 feet longer, and so the length is equal to 50 plus 44, which is 94 feet. So answering this with a complete sentence, the length of a professional of an NBA, it says, basketball court is 94 feet, and the width is 50 feet. All right, so I guess we already answered C and D. Jumped ahead of myself a little bit there. Now in problem 8, we're going to solve each of the following formulas for the variable specified. And so we have a perimeter equation. Perimeter is equal to 2L plus 2W. We want to solve this for W. So we want to get this alone, and that means we're going to subtract the 2L from both sides. And that gives us P minus 2L equals 2W. And the last thing we need to do to get the W alone is divide both sides by 2. That gives us W is equal to P minus 2L over 2. In this next equation, we have V times the quantity P plus A equals K, and we want to solve it for P. So there are a couple of different ways you can approach this. Both of them will give you equivalent expressions that look a little bit different, but they're both equally as correct. So one thing that you could do, because you want to get this P alone, and you have V times this quantity, is that you could divide both sides by V. And that would give you P plus A is equal to K divided by V. And we're trying to solve for P, so the last step then would be to subtract A from both sides. So we would get P is equal to K divided by V minus A. So that's one way that you could approach it. The other way that you could have started this out was to distribute the V, giving you VP plus VA equals K. And we're trying to get the P alone, so we're going to subtract the VA from both sides. That gives us VP equals K minus VA. And then we're getting solving for P, so we're going to divide both sides by V. And that gives us P is equal to K minus, and most of the time we write variables in alphabetical order. So we're going to write that as AV and then divided by V. So again, these expressions look a little bit different, but they're really equal to each other. Okay. In our next one here, we have W equals 110 plus 11 halves times the quantity H minus 60, and we want to solve this for H. Okay, so we're trying to get this H alone. So the first thing that I'm going to do is I'm going to add this 110, or subtract 110 from both sides. So on the left I'll have W minus 110, and it's equal to 11 halves times H minus 60. We're trying to get H alone, so I want to get rid of this 11 halves, and right now it's being multiplied by to this quantity, and so I'm going to divide both sides by 11 halves. And multiplying, or sorry, dividing by a fraction is the same as multiplying by its reciprocal. And so what this will become is 2 over 11 times the quantity w minus 110. So now I'm multiplying by this fraction flipped upside down, its reciprocal. And these 11 halves cancel. So on the right now I'll just be left with h minus 60. One more thing to do, and that's to add 60 to both sides. And that will give us h is equal to 2/11 times the quantity w minus 110, and then plus 60. So we could simplify this a little bit. You could distribute the 2/11. That will give us h is equal to 2/11 w minus, and when we multiply 110 by 2/11, so let's just do that on our calculators. So we're taking, 110, and we're multiplying that by the fraction, and so because it's a fraction, put it in parentheses, 2 divided by 11, and close your parentheses, and then hit equals, and we get 20. And then we have plus 60. So we get h is equal to 2 divided by 11 times w, so 2/11 w, and then negative 20 and positive 60 gives you plus 40. So this looks a little bit nicer than this formula that we have up here. And this way that I solved this problem is not the only way that you could have approached this. You could have distributed the 11 halves right away, and that would have gotten you to this answer down here as well. So either way is fine. As long as you don't break any algebra rules or any, break the rules of PEMDAS, then you'll be fine. So now we want to solve each of the following equations for x, and then check our answer back up in our original equation. So we have 2x plus 9 equals 15x minus 12. So I'm going to gather up all the x's on the left and the plain old numbers on the right, so I'm going to subtract 5x from both sides. And 2x minus 5x is negative 3x, and then we have plus 9 equals negative 12. And now we're going to get all the plain old numbers on the right, so that means I have to subtract 9 from both sides. That gives me negative 3x equals negative 21. And lastly, we divide by negative 3. And that gives me x is equal to 7. So I always put a little check mark when I'm doing my checks, and what I want to do is I want to plug 7 into x up into my original, so I'm going to write just a shell down. 2 times a blank set of parentheses plus 9 equals 5 times a blank parentheses minus 12. And I want to figure out, is this going to give me a true statement when I replace the x with a 7? So 2 times 7 is 14, and then we have plus 9. So is this equal to 35 minus 12? Well, 14 plus 9 is 23. And 35 minus 12 is also 23, and so it is true. In our next example, we have 21 minus x equals negative 3 minus 5x. So again, I'm going to gather up all the x's on the left and the plain old numbers on the right. So I'm going to add 5x to both sides. So I have this 21. And then negative x plus 5x is plus 4x. And then we have negative 3. Now I want all the plain old numbers over on the right, so I'm going to subtract 21 from both sides. That gives us 4x is equal to negative 24, and then we're going to divide both sides by 4. That gives us x is equal to negative 6. Now we want to check. And so again, I'm going to write down the shell. So I have 21 minus, I'm going to do an empty parentheses for the x, and it's equal to negative 3 minus 5, and then an empty parenthesis again for what I got for x. So I want to know, is this true when I replace the x with negative 6? And so I'm going to add my question mark above the equal sign because I'm trying to determine if this is true or not. So 21 minus a negative 6, remember when you're subtracting a negative, it becomes addition. And so 21 plus 6 is 27. And then over here we have negative 3, and negative 5 times negative 6 is positive 30. And so 27 is in fact equal to negative 3 plus 30. And as soon as you can see that this statement is true, you can stop at that point. And I always put a big capital T indicating that, yep, it actually did work. In this next example, we have to simplify this left-hand side, and to simplify that, we need to distribute the 2. We have to multiply it to the x and to the negative 3. That will give us 2x minus 6 is equal to negative 8. The only variable I have is over here on the left, so I'm going to gather up all the plain old numbers on the right, and I'm going to do that by adding 6 to both sides. That gives us 2x is equal to negative 2, and then when we divide both sides by 2, we get x equals negative 1. Now I'm going to check to see if this solution works, and we have 2 times a parentheses, and that's x minus 3. I'm going to have a blank set of parentheses there for what I'm putting into x, and then minus 8. And I'm checking to see if that's true when I replace the x with a negative 1. So we need to do inside parentheses first. That'll give us 2 times the quantity. Negative 1 minus 3 is negative 4, and that is in fact equal to negative 8. And so our solution worked. In our next one here, again, we have to simplify the left-hand side of the equation. We need to distribute this 2, multiplying it to the x and the negative 4. That gives us 2x minus 8, and then we have plus 6 equals 4x minus 7. We have two like terms now here. We have negative 8 and positive 6. That's 2x minus 2 equals 4x minus 7. Gather the x's up on the left. I'm going to subtract 4x from both sides. 2x minus 4x is negative 2x, and then minus 2 equals negative 7. Now add the 2 to both sides. We get negative 2x equals negative 5, and then divide by negative 2. We get x is equal to 5 halves. Again, we want to check this. So we're going to have 2 times the quantity and then an empty set of parentheses for what I got for x, and then minus 4 plus 6. We want to know, is this equal to 4 times x, so leave an empty set of parentheses, and then minus 7. And in the parentheses, we're going to write what we got for x, which was 5 halves. So over here, compute what's inside the parentheses. So 5 divided by 2 gives us 2.5, and then subtract 4 gives us negative 1.5. So we have 2 times, and that was negative 1.5. Plus 6, is this equal to, when you multiply 5 halves times 4, the 2 goes into the 4 twice, and so you get 10 minus 7. And you can do that on your calculator as well. And so 2 times negative 1.5 is going to be negative 3. And 10 minus 7 is 3, and negative 3 plus 6 is also 3. So we did get a true statement, and our solution worked. So just two more problems to solve here. And so we need to simplify the right-hand side, which means we're going to distribute this 4. That gives us 12x minus 9 equals 24 plus 12x. And always get your x's in place first and then do the constants. So I want to move all of the variables over onto the left-hand side. So I'm going to subtract 12x from both sides. And so now 12x minus 12x is nothing, and so I'm left with negative 9 equals 24. Negative 9 is not equal to 24. This is false. Whenever you're solving an equation and you get a false statement like this, what it means is that there's no solution. There is no value of x that we can plug into here that will give us a true statement. So you cannot find a number to replace this x, these two x's with, that will make this equation true. So no solution would be our answer here. Now this time we have to simplify on both sides of our equation. We're going to distribute the 2 on the left and distribute the negative 4 here on the right. So 2 times 8x is 16x, and 2 times negative 4 is negative 8, and then we have plus 10 equals 22, and then negative 4 times 5 is negative 20, and negative 4 times negative 4x is plus 16x. So again, we have negative 8 and positive 10, so that's 16x plus 2. And we have 22 minus 20, which is 2, and then plus 16x. And we're going to subtract 16x from both sides to gather up all of our x's on the left. And again, remember to do the x's first always. And 16x minus 16x is nothing, leaving us with 2. And over here we also have a 2. So this time we solved and we got a true statement. So 2 is equal to 2. That's true. And so what that means is that any value that you put in for x will give you a true statement. It won't matter what you could put 0 in there, negative 3.8, negative 7.5238, whatever you want. Any number you can dream up, you can put into x, and it will give you a true statement. And so all real numbers. So any real number you can dream up, if you plug it into this, will give you a true statement. And that concludes our lecture. Let me know if you have any questions.